Welcome to this first lesson about electric fields. So let's begin with what exactly they are. So an electric field was first thought of by Michael Faraday, who hypothesized that charged objects exert a force on all charged particles in its area. And this hypothesis has been proven true as we've come to learn more about electric fields. We now see electric fields as electric force per unit charge. A charge is always giving off an electric field. It does not need another charge in its area, which is an important fact you need to remember. Electric fields are similar to gravitational field strength, as gravitational field strength is the effect a mass has on the regions around it, while an electric field is the effect a charge has on the area around it. Now let's look at the two main formulas used to calculate electric field. The first one being E equals kq over r squared. The E in this formula is equal to electric field, which has units of newtons over coulombs. The K in this formula is equal to Coulomb's constant, which is equal to 9 times 10 to the 9, and the units are newtons times meters squared over coulomb squared. Q is the variable used to represent source charge and has units of coulombs. A source charge is the charge around which the electric field forms. The last variable is r, or radius, and the units used to represent this are meters. The other formula is E equals F over Q, also having absolute values on both sides. The F in this formula represents electric force and has units of N, and E is also the same as the previous equation, also being equal to electric field. However, in this formula, a lowercase q is used, which is equal to test charge, which is the charge whose electric field were not being measured. The unit for electric field again is newtons over coulombs. And again, it's important to remember that both sides in both of these equations are placed in absolute values due to electric field being a vector, which means it has direction and magnitude. Now, looking at this down here in the blue, we can use the units from all these different variables to verify that both sides equal each other. So if the right side using all these units from these equals to newtons over coulombs, we know this is in fact equal to electric field. So from the Coulomb's constant, we get newtons times meters squared over coulomb squared. And due to this being multiplied by a coulomb, one of the coulombs cancels out. And we're left with newtons times meters squared over coulombs over meters squared. But the meters squareds both cancel each other out, leaving us with just newton over coulombs. Now let's verify the other equation similarly to how we did this one. So the unit of force is newtons and the unit of Q is coulombs, leaving us with newtons over coulombs. And now let's show how both of these formulas are equal to each other. Force is equal to kq times lowercase q over r squared. So if we plug that into this equation, we get kq times lowercase q over r squared divided by lowercase q. This cancels the lowercase q's out, leaving us just with kq over r squared, which is back to this equation, showing how both are the same. Before we move on to doing some practice questions related to electric field, we first need to fully understand direction as it's extremely vital. So, while working with the electric field, and if the source charge is negative, that will cause it to pull radially inwards. And if the source charge is positive, that will cause it to push radially outwards, as shown in these two diagrams here. Another important fact that needs to be remembered is a test charge has no influence on the direction of electric field. So if my red dot, for example, was a test charge and it was positive, it would have no effect on the electric field. All that matters is your source charge. So now let's look at this. A positive test charge experiences electric force and electric field in the same direction, as shown in this diagram below, because a positive test charge is attracted to the negative source charge, and a negative source charge also has a electric field radially inwards. However, with a negative test charge, it will experience electric force and field in opposite directions, with electric field being towards the negative source charge, but due to like charges being repelling, it causes a force to the left. If we look at this picture, we can see what happens when there's two charges placed next to each other, and these two charges have the same charge, in this case both being positive. You can see as with this, both of the two positive charges push outwards, creating this spot in the middle where it has no electric field, because of both of the electric fields are canceling each other out due to both of them pushing on any charge that would be placed here, giving it a net electric field of 0. While if I was here and I was a charge, I would experience an electric field going to the left. This other picture is of what happens when you have two charges generating electric fields that are of different charges. So if you have a positive charge and a negative charge, due to negative charges pulling radially inwards, in the middle all the charges will be going towards the negative charge, and on the right side if there's a charge here, they'd be being pulled towards the negative charge, while if you're on the left side and there's a charge here, all of them would be pushed more to the left, as the positive charge will push radially outwards. Before we move on to doing practice questions related to both magnitude and direction for electric field, we're first just going to focus solely on direction to truly understand that we are getting it. So when we have a positive source charge and a test charge up here, what will be the electric field acting on this test charge? The electric field acting on this test charge will be upwards. And the reason this test charge has no charge is because it does not matter, due to me mentioning before that test charges have no effect on electric field. The charge of a test charge has no effect on electric field. Now let's move on to the second question. When we have a negative source charge and a test charge on the right, what will be the electric field acting on this test charge? It will be towards the left due to negative source charges pulling radially inwards. Now let's look at the third practice question. When we have a positive source charge and a test charge to the left and underneath it, it will cause an electric field acting on the test charge to be to the left and down, due to positive source charges pushing radially outwards. Now, if we have a second test charge, what will be the electric field on this? It will actually be the same as the electric field on the first charge, also being down and to the left. But to expand on this, let's say if the radius of test charge 2 is double that of test charge 1, how much smaller is the electric field? So to calculate the electric field of test charge 1, we would use this formula that we've learned about before. But to calculate the electric field of test charge number 2, due to us knowing it's double the radius, we just put a 2r, like in this formula. And by using this, we can find out the electric field is 1/4 of what it was before. So it's 4 times smaller due to radius being squared in this formula. This shows by moving farther away from the source charge, the magnitude of electric field will get smaller. Now let's move on to the final question, where we have a positive source charge and a negative source charge acting on this one test charge. What will be the direction of the electric field on this test charge? So the direction on this test charge will be to the right, due to the positive source charge pushing radially outwards and the negative source charge pulling radially inwards. The positive source charge pushes downwards and to the right, while the negative source charge pulls upwards and to the right. The electric field from the negative source charge pulling up and the electric field from the positive source charge pushing down will cancel each other out, leaving only an electric field to the right. Now let's apply all of what we've learned before to do some calculations. So example 1, find electric field and direction 10 centimeters west of -2 microcoulombs. So here is a diagram of the situation, and we're going to use this diagram to answer this question, as it helps us visualize it. We can tell direction using this diagram due to us knowing negative source charges pull radially inwards. So in this case, the charge will cause this point to feel an electric field to the east. Now let's calculate the magnitude. So step 1 is to first get the formula we are going to use for this. And due to us knowing the magnitude of the source charge, we're going to use E equals kq over r squared. So step 2 is to plug in all the values that we know. And due to it being 10 centimeters to the right, we have to change that to meters due to us using meters in this formula. So that is equal to 0.1 meters. And then we use our Coulomb's constant times our source charge's value divided by our distance, and we get an answer of 1.8 times 10 to the 6th newtons over coulombs. And we already calculated the reason why it's east. Now let's do example number 2. In this question, we are going to find electric field and direction if an electron experiences a force of 3.2 times 10 to the negative 16 newtons north. So here is a diagram used to represent this situation. An electron can be experiencing a force upward in two scenarios. Either there's a positive source charge north or there's a negative source charge south. In both scenarios, the direction of the electric field is the same due to a positive source charge generating electric field radially outwards, which causes the electric field affecting the electron to be south. And in the other scenario, a negative source charge would generate an electric field radially inwards, which would also cause the electric field affecting the electron to be south. Remember, electric field has nothing to do with test charge. It's all dependent upon its source charges. Now that we know its direction, we can begin looking at its magnitude. So, step 1 is to look at the information we're given, and due to us being given force, we're going to use E equals FQ as our equation. In step 2, we plug in the values we're given, so we're going to plug in our force in the force law, and due to electrons having a charge of 1.6 times 10 to the negative 19, we're going to plug that into the Q spot. And due to this being placed in absolute values, the negative of the electron really doesn't matter. So in step 3, we then calculate this, and we get 2 times 10 to the 3 newtons over coulombs south. And the south was found at the start. Moving on to example number 3, we are going to find the polarity and magnitude of a charge that gives off an electric field of 4 times 10 to the 3 newtons over coulombs left on a point 2 meters to the right. So here is a diagram for this question, and this will help us determine the polarity of the charge. From this diagram, we can see the electric field affecting the point that is 2 meters to the right is left, and for that to happen, the source charge must be negative as it's pulling the point inwards. Now let's move on to calculating the magnitude. So from the information we're given electric field, but we're also given radius. So we know we have to use E equals KQ over R squared. Now we're going to plug in all the numbers, and the variable we're looking for is Q. So we're going to isolate that by timesing the 2 squared over and dividing by the 9 times 10 to the 9, which creates this. Q equals 4 times 10 to the 3, which is equal to our electric field, times 2 squared, which is our radius, divided by our coulombs constant. And in step 4, we get the answer, which is equal to 1.78 times 10 to the negative 6 coulombs. And the reason it's negative is due to us determining the polarity of the charge must be negative. Now let's get into some harder calculations. In example number 4, we are going to find the electric field a proton experiences if it has a 2 microcoulomb charge 2 meters to the left and a 3 microcoulomb charge 3 meters to the right. Let's begin by first looking at the direction the electric field will be going. A 2 microcoulomb charge is positive, so the electric field it generates will be radially outwards, causing the proton to experience an electric field to the right. The 3 microcoulomb charge is also positive, causing it to also push radially outwards, making the proton experience an electric field to the left. To figure out the overall direction of the electric field, we will first need to calculate the magnitude of the two fields. So, to find the magnitude of the 2 microcoulomb charge, we are first gonna use the formula E equals KQ over R squared due to us being provided information that would lead us to use this formula. So when we plug all the values in that we're given, with us already knowing Coulomb's constant, and then we plug in the 2 times 10 to the negative 6 from which we are given, and the 2 meters that it is away from the proton, we plug this all in and we figure out that it will cause it to experience an electric field of 4,500 newtons over coulombs east. And now when we look at the 3 microcoulomb charge, we can find out using the same formula but plugging in the values for that by plugging in 9 times 10 to the 9, which is coulomb's constant again, times the 3 times 10 to the negative 6, which is equal to 3 microcoulombs, and the 3 meters distance that it is away from the test charge, which is being squared. We can then calculate that using our calculators to find E equals to 3000 newtons over coulombs west. Due to the 2 microcoulomb generating due to the 2 microcoulomb source charge generating a greater electric field, it will create an overall direction to the east or to the right, as it has a greater strength and a greater electric field. And due to electric field being a vector, we are going to use vector addition. So we are going to do the 4500 from this plus the 3000 from this to figure out that we're experiencing an 1500 newtons over coulombs electric field towards the east. Moving on to example number 5, a 2.5 millicoulomb charge initially at rest is placed in a vertically upwards 2250 newtons over coulomb electric field. If the mass of the particle is 125 grams, find A, the net force on the particle, and B, its speed after 2.5 seconds. For this question, we're first going to begin by solving its magnitude. In part A, we use E equals Fe over Q, which is just electric force, due to us needing to find electric force. In step 2, we plug in the numbers that we know, so we know the electric field and we know the value of the test charge. And we isolate for our force electric by moving the 2.50 times 10 to the negative 3 over. This leads us to knowing that Fe is equal to 2250 times 2.5 times 10 to the negative 3, which is equal to 5.625 newtons upwards. And the reason the direction is up is due to a positive test charge experiencing electric force the same direction as electric field, and due to electric field being up, electric force is also upwards. In step 5, we need to find Fg, which is equal to force gravity. And force gravity is equal to 9.8 times 0.125, which is our mass. So the value of gravity times our mass will give us our force gravity. And from this, we find that our force gravity is equal to 1.225 newtons down. The reason the direction is down is because it's due to force gravity causing it to be pulled down. Now we are going to use vector addition to figure out the net force. In step 7, we find its net force by doing 5.625 plus negative 1.125 due to gravity being in the opposite direction. This leads us to finding that Fnet is equal to 4.4 newtons upwards. Now we are going to try to find its speed after the 2.5 seconds. Due to us knowing Fnet, we can now use Fnet equals ma. So we plug in our numbers. 4.4 equals 0.125, which is our mass, times acceleration. And we isolate for acceleration, causing us to do 4.4 divided by 0.125, which leads us to find our acceleration is equal to 35.2 newtons upwards. Now that we have acceleration, we can use this kinematic equation, which is v final equals v initial plus acceleration times time, to find our v final. And due to us initially starting at rest, we know our v initial is 0. So we just do our acceleration times the value of time we are given to find our v final, which leads us to find that our v final is equal to 88 meters per second. We are now on our final example, which is example number 6, in which we will need to find the resultant electric field and direction at point X. This is point X, shown in this diagram. This question, we have to look at the diagram as all the information is provided in it. I know it's a little hard to see, but that's why I will be also voicing out and telling you what the values are. So we first need to look at our 4 nanocoulomb charge and notice that the electric field for this will be north due to a positive source charge generating an electric field radially outwards. And then we need to see our negative 2 nanocoulomb charge and notice that the electric field it will be generating will be to the east due to negative source charges generating an electric field radially inwards. The distances provided here are both 0.5. So now we are going to start calculating the magnitude, starting with the negative 2 nanocoulomb charge. And we are going to use the formula E equals kq over r squared. And we do 9 times 10 to the 9 times negative 2 times 10 to the negative 9 over 0.5 squared. This will give us an electric field of 72 newtons over coulombs east. In step 4, we are now going to calculate the electric field created by the 4 nanocoulomb charge. And we are going to use the same formula as used previously. And we're going to do 9, and then we're going to plug in our values, and we plug in 9 times 10 to the 9 times 4 times 10 to the negative 9 divided by 0.5 squared to find our electric field. And this gives us an electric field equal to 144 newtons over coulombs north. And we use this now to create a new triangle. And we need to find the missing side to find our net electric field. So we do 72 squared times 144 squared, which is equal to 25,920. And this number is then square rooted to find our net electric field, which is equal to 161 newtons over coulombs. Now that we found our net electric field, we also need to find its direction. So to find its direction, we are going to do our 72 over our 144, and we're going to tan negative 1 that. So we do tan negative 1, 72 over 144 to find this angle. And the direction we are given is equal to 26.6 degrees east of north due to going to east and north, and the angle being 26.6 degrees. In step 12, we write out our final answer being E is equal to 161 newtons over coulombs at 26.6 degrees east of north. Here are some real-life examples of how electric fields are used. Firstly, electric fields are generated when a wound is formed and help in the healing process by attracting cells such as keratinocytes, fibroblasts, macrophages, and lymphocytes that help fight to fix the wound. The image on the right is of an electric field and its purpose in stimulation. Electric fields are used for stimulation all across the body and can help stimulate muscles and which help in their healing process. But I mainly want to focus on how they're used in stimulation for the nervous system. So electric fields can be used to stimulate and suppress neural activity. This is being used to stop endogenous signals that can cause Parkinson's disease, tremors, or epileptic seizures. Finally, using pulsed electric field, food can be preserved in a way that has a minimal influence on food quality. So these are just 3 different ways of how electric fields are being used in real life and why it's important to learn about it. So this is the end of the lesson, but I just quickly want to show a website in which you can mess around with an electric field. But before I do that, I just want to remind you to ask me any questions you may have. Talking about it is a simulation website in which you can generate different electric fields. So here's the electric field created by a positive charge. We've already talked about how it's radially outwards. And then here's the electric field created by a negative charge. Again, we talked about how it's radially inwards. And this is just a website you can use to demonstrate that. And it also comes with many other tools that are also helpful. So this is, again, I showed an image of this, what happens when there's two unlike charges and the electric field that's created being radially inwards toward the negative charge and radially outwards toward from the positive charge. And now we can see what happens when there's two negative charges. How do you see how both of them are towards themselves? And in this middle point where it's blackened out, that means that the net electric field there is getting closer to zero. And this yellow thing, is actually a sensor, or yellow dot. And it can help us see the direction that the electric field is. When we have a charge and we get closer to it, we can see the value growing, which is another thing you can get from the side. By having the value grow, that means when you get closer to the charge, your electric field grows and it gets stronger. The reason the unit of this is in volts over meters is because it's a formula you'll learn about later when you get more into voltage and volts and all that. But it is the same as saying newtons over coulombs. We also have a volt generator, volts checker, which you can use for later, and something that you can use to even check distance. So when we have 130 centimeters, we can figure out, or we're 60 centimeters away from this charge. When there's two different charges, we can check the electric field that will be acting on this if there's a test charge here. So this website's really helpful as it lets you just experiment with many different scenarios and expand your knowledge on electric field. We can add grids, we can add voltage, we can do many different things with this website, and that's why I recommend you use it to expand your knowledge of electric fields, as you can test many different scenarios. That concludes this video, and I hope you guys learned something about electric fields.